Hi, and hello to all of you. So it's been a while, no, that we will solve some problems. So as you can see, we already have our long hair. So new attire and new hairdo. Okay, let us move forward to another problem, which is problem number 4. Okay, let's read the problem first. A three-phase line has a series resistance of 10 ohms per wire and a reactance of 80 ohms per wire. The load current is 90 amperes and the power factor of the load is 80% lagging. The sending end voltage of this line is 44 kilovolts. So what is the receiving end voltage and the power factor? Okay, let us move on to our solution here. So, in order to solve this problem, a very interesting problem which is correlated with problem number 2. As you can see here, we need to use a PPA or per phase analysis, and this line is a three-phase, three-wire line. And then from there, we need to use per phase analysis, which is we consider the system as balanced. So, we consider, okay, your VSN here, VRN, and your transmission line, I could say ZTL. And then your VSN here is 44K all over square root of 3 in terms of magnitude. But again, there's no angle here since we will consider the receiving end voltage as our reference. So you have here 10 plus J80. The power factor, by the way, is 0.8 lagging. So in order to get the angle, you need to have the cosine inverse of your 0.8. And then from our Cisco table, since this is lagging, you consider the angle of your theta I as negative 37. Now you have 10 plus J80 per phase, no, of your R and JX. And our main goal here is this, no? This is our required on the problem. What is VRN? Okay, for VRN, we have this solution. Just recall our short line. By the way, this is a three-phase, three-wire short line. Approximate. Since the given is R plus JXL only. So, we have here VSN, var alpha, which is the transmission angle, VRN, bar 0 as reference, IR, and ZL. Now, from the other problems, we have already done this equation here. So what we'll do is just substitute. The 44K over square root of 3 is simply equal to 25.404K. And then bar angle alpha. And then this one, in terms of rectangular, VRN plus J0. And then you have your current I, since your current IR here is also equal to your IS. Okay, definitely they are in series, so you have here 90 bar 36.87, and then your ZL, as usual, R plus JX, 10 plus J80. So a little bit of simplifications. Okay, we have here VRN plus J0, but this J0 is 0, so we can already eliminate that. Then 90 bar negative 36.87 multiplied by 10 plus J80, the answer is 5040. 0.009 and plus 5219.99. So what I've done here is I just already include the real and the imaginary parts separately. Now we need to separate again, like problem number 2, the real and reactive terms in order to solve for VRN. So just recall, okay, so this is Z squared is equal to the real part, okay, plus the reactive part squared magnitude. Okay, thus, like problem number 2, all you have to do is get only the magnitude parts of this equation here, which is 25.404K squared, VRN plus 5040.4009 squared, plus there's no reactive component. So, in this case, you have 5219.99 squared. Only the real part. Okay. Okay, now in this case, you have there the squared, so you need to subtract this one, then squared, and then as you can see, the result is a linear relationship. You can now get VRN. Okay, by solving it, VRN is 19.82, 1 kilovolt. And doing the balanced polyphase, getting the line, square root of 3 VRN, the answer for letter A, okay, later we will solve power factor, is 34.33 kilovolts. So, stay tuned for letter B. Okay, so we are on letter B on problem number 4. So, on problem number 1, we solve for VRN. Okay, now, letter B needs the power factor descending end. So, we will use the formula here. We already go to the solution part. We'll make use of the formula again of VSN is VRN bar 0, and then your current I, ZL. So, VRN plus the drop, which is I and ZL. Since the current and the ZL is already given and VRN is already defined from A, so we can now solve for VSN. So recompute this again. The answer is 25.403. Bar angle positive, this is a positive value, 11.85, 78 kilovolt. Okay, so our main goal here is the power factor angle, and please take note the power factor angle will be dependent. Okay, again the power factor is cosine of the angle theta, and the theta will be dependent on whatever the angle of the voltage and the current is, but it will depend on the sending end as expected because we need to get the power factor of the system. Now we will use our technique. I think we already described it on problem number 1, the EBD, or the so-called electric body diagram. So, we will make use of the phasor diagram in order to solve for the angle, and then as well, what is the condition of that angle. Please take note, if you're considering phasor, we're considering what is the characteristic or the behavior or condition of the angle. Now, in this case, VSN has this value here, and this is your alpha. And then we also recall IS, 90 bar negative 36.87 degree ampere. So this is your theta I, definitely. And this is your theta S, KVS. With respect, again, all of the angles, with respect to bar angle 0 of your VRN. Okay, with respect. Now, in this case, you have 11.85, no, positive. So it is in counterclockwise direction. Here, the angle theta I is 36.87 negative. Okay, clockwise direction. The angle between the VS and IS is your theta here. And please take note of the behavior of the angle here. Okay, considering VSN as our reference, and IS will be the rotating phasor. So in this case, okay, that rotation here means in a lagging condition. Okay, so it means IS lags VS by a certain angle, theta rather, which means the power factor is expected to be lagging. So adding 11.58 and 36.87, which is evident, the answer is 48.72 degree, and thus having the power factor as cosine of the angle theta, we have 0.6596 lagging. Now there is another way. Okay, if you're listening from our past lesson, in terms of power factor angle condition. This for short line only, for short lines. That if the power factor of the sending end, okay, which is this, is less than the power factor at the receiving end, therefore we could consider this one as lagging. Or the power factor of the sending end is greater than the receiving end, you consider the power factor of the system, the source side, as leading condition. So there are many ways in determining the condition, but I usually prefer 110% sure this phasor diagram in terms of electric body diagram, in terms of voltage and current. Okay, we already described number 4. Let's move forward to number 5. See you.